The research paper discusses the development of a novel timing detector, the Picosec Micromegas, which is designed for precise timing in high-energy physics experiments. This detector utilizes a Cherenkov radiator coupled to a semi-transparent photocathode and a Micromegas amplification structure. The initial prototype achieved a time resolution below 25 picoseconds (ps). To enhance the design for large area coverage, a 19-channel multipad prototype was created, but it suffered from non-uniformity issues in the preamplification gap, leading to degraded timing resolution. To address this, a new 100 square centimeters detector module with 100 channels was developed using a rigid hybrid ceramic FR4 Micromegas board to improve drift gap uniformity. Measurements with 80 JV/c muons showed improvements in timing response across measured pads, resulting in a time resolution below 25 ps. Further advancements were made with a thinner drift gap detector module and newly developed RF pulse amplifiers, enhancing the resolution to 17 ps. This paper presents the development of the detector from structural simulations, design, and beam test commissioning, focusing on the timing performance of the thinner drift gap detector module in combination with new electronics. An automated timing scan method was used for these measurements. The study also explores various micropattern gaseous detectors such as MSGC, GEM, THGEM, RETHGEM, MHSP, MICROPIC, MICROMEGAS, INGRID, etc., and their applications as timing detectors and Cherenkov detectors. The research team involved in this project consists of experts from various institutions worldwide, including the Ruder Boskovic Institute, Aristotle University of Thessaloniki, Friedrich Alexander Universität Erlangen-Nuremberg, CEALIST, Diamond Sensors Laboratory, CSACLE, Center for Interdisciplinary Research and Innovation, CIRIAUTH, National Technical University of Athens, Bursa Uludeji University, University of Virginia, and others. This collaborative effort aims to advance the field of precise timing detectors for future high-energy physics experiments. The development of precise timing detectors with large area coverage and high radiation fluence capabilities is a significant challenge for future physics experiments. Picosec Micromegas, is a gaseous detector designed for precise timing applications, achieving a time resolution of tens of picoseconds. The detector consists of an amplification structure coupled to a Cherenkov radiator with a CSI semi-transparent photocathode, operating as a two-stage amplification structure with a working gas mixture of Na, C2H6, CF4, 80 hours 10 minutes and 10 seconds. A single-channel prototype demonstrated excellent time resolution below 25 ps for minimum ionizing particles, MIPS, measurements. However, a multi-channel detector with 19 hexagonal pads suffered from drift field non-uniformity, which was investigated and corrected using flatness corrections based on particle hit position. The detector achieved a time resolution of 25 ps in the best case after applying corrections. To produce a larger multi-pad Picosec, new design procedures were introduced, focusing on improving flatness and uniformity of the drift gap. Structural mechanics simulations of the mesh tension interface and coupling to the detector casing were performed to select a substrate ensuring planarity better than 10 micrometers over 100 square centimeters active area. A more rigid and thicker PCB was suggested, fabricated as a combination of 4 by 1 mm thick ceramic core with 0.3 mm thick FR4 outer layers. The ceramic core provided rigidity, while the thin FR4 layers enabled classic PCB manufacturing, precise flattening, and polishing. The readout structure was arranged in a 10 by 10 matrix of square pads, with signal routing to SMB connectors on the top of the outer board, OB, via spring-loaded pins. The compressive force of the spring-loaded pins ensured the radiator was pressed firmly and evenly into the positioning groove in the chamber. The time response of the 100-channel detector under test, DUT, to 80 JV muons was measured at the CERN SPSH4 secondary beamline, using a triple GEM detector telescope for particle hit position information and MCPPMTs as a timing reference or trigger. The detector's timing performance is evaluated using a high-bandwidth CIVIDECC2 amplifier and a Lecroy WR8104 oscilloscope, digitizing the signal at 10 Gs. The recorded waveforms are analyzed using methods described in previous publications. Initial measurements with a prototype detector featuring a 220 micrometers drift gap thickness and a CSI photocathode on a thin crossing layer demonstrate a time resolution below 25 ps for each pad in its central 5 mm by 5 mm area. To further improve timing, the dependence of the signal arrival time, SAT, on the electron peak charge is taken into account as a timewalk correction. Uniform drift fields across the pad surface would result in consistent timing characteristics for all pads, enabling the use of a single global time walk correction function. Timing measurements from 7 pads in the same row show that all pads closely follow the timewalk correction function, indicating consistent global behavior. Measuring the timing performance of large area detectors poses a challenge in selecting a reference detector with better timing characteristics and spatial uniformity. Large area MCPs are available but are more expensive, and their timing performance must be known to avoid biasing the DUT response measurements. A modification to the measurement method involves using the central part of the MCP as a trigger and time reference with a high threshold to reject events from the outer region. An automated scanning method is employed to cover the large DUT area with the central part of the MCP, moving on a grid of 2.5 mm by 2.5 mm every 1,000 recorded events. The method benefits from reduced load on the tracking system and oscilloscope recording but is time-consuming due to the geometric scan. This approach can be employed for measurements on a single pad, signal sharing, or entire detector scan studies. Earlier measurements and simulations indicate that reducing the drift gap thickness improves the time resolution of the Picosec. Subsequent beam test measurements with custom electronics and a 180 micrometers drift gap thickness aim to validate these findings. The development of a new 100-channel Picosec Micromegas detector with an area of 100 square centimeters aimed to achieve a flat and uniform drift gap, ensuring uniform timing over a large area. A prototype based on an embedded ceramic board confirmed the uniformity and preserved the time resolution of the single-channel detector. The drift gap thickness was reduced to 180 micrometers, and timing tests with a newly developed custom RF amplifier were conducted. Measurements were performed during 2 RD51 beam test campaigns in July and October 2022. The RMS of SAT values for tracks passing through the 4 mm by 4 mm pad central area during the scans are summarized in tables 1 and 2. SAT distributions of all measured pads show RMS values of 17.1 ps on average. The dependence of the SAT and time resolution on the E-peak charge was also investigated, and a similar behavior to the prototype with the standard drift gap detector was found, as shown in Figure 5. The timing method for characterizing larger areas was implemented and used for measurements. Scans of 10 different pads with a readout chain based on custom amplifiers and oscilloscopes show excellent time resolution, averaging 17 ps for all measured pads. The first results show uniformity of the detector with a shorter drift gap. New developments are underway to improve stability and robustness and to develop a full readout chain with a multi-channel SAM-PIC digitizer. The detector's performance was evaluated using various metrics, including the RMS of SAT values, time resolution, and E-peak charge dependence. The results demonstrate the detector's ability to maintain uniform timing over a large area, with a reduced drift gap thickness. The custom RF amplifier and readout chain played a crucial role in achieving these results. Future work will focus on improving the detector's stability and robustness, as well as developing a full readout chain. The research was supported by various funding agencies, including the EPR&D, CERN Strategic Program on Technologies for Future Experiments, and the RD51 collaboration. The authors acknowledge the financial support and collaboration with various institutions, including CERN, Université Paris-Saclay, and the Chinese Academy of Sciences.